So far we have seen the describing function of several different types of nonlinear behaviors, and now we'll start with the analysis portion. And in this first video lecture on this analysis using describing function, we'll be seeing how describing function can be used for finding out the existence of a limit cycle in nonlinear systems. So we'll consider a system which we know exhibits the property of limit cycle, and consider a van der Waals oscillator. X double dot plus mu x square minus 1 x dot plus x equal to 0. Let this be equation number 1. We already know that van der Waals oscillator exhibits the property of a limit cycle, but we want to see this through the describing function. In order to we need to first of all be able to represent this van der Waals equation through a nonlinear element that we which we already know the describing function. To do that, we'll represent this equation number 1 through block diagram. And what this block diagram will do is it will indicate the nonlinear element and the linear blocks. Separately. So our equation is x double dot minus mu x dot plus x, and we are also left with mu. So we have an equation here. The van der Waals equation, x double dot plus mu x square minus 1 x dot plus x equal to 0. Multiply mu and x dot to x square minus 1, we will be getting mu x dot minus mu x dot, and we will get in mu x square x dot. In this equation, the only term that is actually representing the nonlinear behavior is the term x square. So mu x square x dot is separated, and the rest of these three terms, they are written separately. So this represents the linear part of this equation. This represents the nonlinear part of this equation. Now if we have a unity feedback system, then in that case, for a unity feedback system, the overall characteristic equation will be 1 plus GSHS. Therefore, what we can do is we can take out x double dot minus mu x dot plus x common, so this becomes 1 plus mu x square x dot divided by x double dot minus mu x dot plus x equal to 0, or which implies 1 plus mu divided by x double dot minus mu x dot plus x into x square x dot is equal to 0. We are separating again the linear part from the non-linear part of the system. And when we actually will be representing the block diagram, we'll be actually taking the transfer function model that is in the S domain. So we can actually write this as 1 plus mu divided by S square minus mu into S plus X so this will be X of S, that will again be taken common, so this already only remains 1 here. 1 x square x dot. So x dot can be represented again, so we'll see this representation on non-linear part separately. X square x dot equal to 0. So we have 1 plus mu divided by s square minus mu s plus 1, where x of s is taken actually common, and that actually represents the transfer function model of the system by s by xs. So therefore we can now say that we have a system, a unity feedback system, wherein there is a nonlinear block. We'll see that in a moment. And we have the linear element, and the linear element here is mu divided by s square minus mu s plus 1. So this gives us, say for example, it's giving us x, so this x is actually being fed back to the system. So this x goes back into the system, that is actually multiplied again with this transfer function. So this is our block diagram representation, and we can have this input as 0, r equal to 0. So this is an unforced system. So now our non-linear element that we have here, we need to define that, how we can show that x square x dot term in this here. Fine. So from here what we are getting is actually minus x. We are actually sensing x, and since r is equal to 0, minus x is available here. So what a non-linear block will do, a non-linear element is x square into x dot. So this x will go to scaling function. Fine. So this goes to a scaling function, so it becomes x square, and it also goes, this x goes to a derivative, that is d by dt, or you can simply say it is s, and so that gives you x dot. So these two are multiplied, not added. So using a multiplier, you can multiply these two, x square and x dot, and so we are actually adding minus x square x dot here. So this then goes to mu s square minus mu s plus 1, which gives us x, and that x is going back to the system. So now our nonlinear block is characterized by this square and derivative. So where if we say this output here is equal to u, so u is equal to minus x square by x dot is the input to our transfer function to our linear block. So now nonlinear block is characterized by mu equal to minus x square x dot, we need to uh, so with this block diagram, now we'll replace this nonlinear element by its describing function. For the describing function, we need to assume the input as actually x to this nonlinear block is a sinusoidal input. So therefore, xt is equal to is the sinusoidal input going to the nonlinear element. That is equation number 3, and therefore x dot will be equal to x omega cos omega t is 4. Now substituting 3 and 4 in equation number 2, this is equation number 2. X double dot minus mu x dot plus x plus mu x square x dot is equal to 0 is a van der Waals equation, and it's equation number 2. Substituting equations 3 and 4 in 2, what we get is u, that is x square x dot is equal to minus x square x dot minus x omega cos omega t into x square sine square omega t. This is equation number 5. Therefore mu is equal to minus x cube omega divided by 2 1 minus cos omega 1 minus 2 cos omega t divided by 2 this is our sine square omega t that we have broken down into 1 minus cos 2 omega t divided by 2. That 2 that we have already taken outside into into cos of omega t. This is our equation number 5. This is 6. Therefore mu u is equal to minus x cube omega by 2 cos of omega t plus x cube omega by 2 cos of omega t into cos of 2 omega t, which is equal to minus x cube from here u is equal to minus x square x dot. This is our equation number 2. So we are substituting 3 and 4 in equation number 2, that is mu equal to minus x square x dot. So we are getting this minus x omega cos of omega t into x square sine square omega t minus x cube by omega by 2 1 minus cos 2 omega t, and cos of omega t, so we are getting this. So this becomes minus x cube by omega, x cube omega divided by 4 cos of omega t plus x cube by 4 cos of 3 omega t. This is actually cos a cos b, and for cos a cos b we have the formula cos a cos b is equal to cos of a plus b plus cos of a minus b whole divided by 2. So cos of a plus b, we have omega t plus 2 omega t, that becomes 3 omega t, and cos of a minus b, that becomes 2 omega t minus omega t, that is omega t, that becomes x square by omega by 2 into cos omega t. So that's why this is x cube by x cube omega by 4 now, instead of we are actually having 2x cube by omega by 2 into cos of omega t terms. Now looking at this equation, we can say this is our fundamental component and this is our third harmonic component. The describing function therefore is y1 by x. Y1 in this case is minus x square omega by 4 divided by this actually divided by this is minus x cube by omega by 4 divided by x, so it becomes minus x square omega divided by 4. Right? So minus x cube omega by 4 divided by x, it becomes minus x square omega divided by 4. So this is our describing function now. So therefore our system is now this r is still equal to 0 only. We have a describing function minus x square omega by 4, and we have a linear function mu divided by s square minus mu s plus 1. So we are getting the Keres equation of the system is 1 plus g of s into n of m times x equal to 0 now, right? Where 1 plus nx is x square, instead of omega we write s now, divided by 4 into mu s square minus mu s plus 1 equal to 0. Like on solving this, we get s square minus mu s plus 1 plus s mu x square, this capital X square divided by 4 equal to 0. The eigenvalues of the system s1 comma s2 will be equal to minus mu x square minus 4 divided by 8 plus minus under root of 1 by 64 mu square x square minus 4 square minus 1. Fine, so this is minus b plus minus b square minus 4ac divided by 2a. So we are getting this thing. Now for for the system to have to exhibit limit cycle, the poles need to lie, that means it has to have an oscillatory behavior. For limit cycle the input is 0, right? And if this system shows oscillatory behavior, at r equal to 0, that means or what we can say in other words, if this system shows an undamped response for r equal to 0, that means the system is exhibiting the property of limit cycle. Now for that to happen, for lambda for S1 and S2 to be on the j omega axis, what we need to have is this real part has to be equal to 0. That means x square has to be equal to 4, or x has to be equal to plus minus 2, right? And for S1, S2 to be on the imaginary axis, on the j omega axis, x square has to be equal to 2. That means x has to be equal to plus minus 2. And if x is equal to plus minus 2, S1 and S2 will be equal to plus minus j only, and this becomes equal to plus minus 2. X square becomes equal to plus minus 2. This term also becomes 0. This term will also become equal to 0. There will only be minus 1 in the root. That means we have plus minus j as the eigenvalues of the system. So for x equal to 2, as well as what will be the frequency of oscillation of the system, the Kerres equation will become s square minus mu s plus 1 plus s mu 4 divided by 4. This becomes only equal to this is our Kerres equation. From here, this is our equation. Substitute x equal to 2 here, so this becomes plus minus 2. So substituting x equal to plus minus 2 will get this equation, or in other words, s square plus 1 equal to 0, because this and this cancels out. That means again s is equal to plus minus j will be the output of this equation. So this system, and you can say omega n is equal to under root of 1, that is equal to 1. So this system will exhibit the property of limit cycle for x equal to 2, and this actually shows how we can actually find out limit cycle in the system. For if any condition that it does not meet the requirements for the undamped response, then we can say that this system will not show the property of limit cycle. But in this particular case, we are seeing that a limit cycle will exist in the system for some particular case. This is how we can examine the existence of limit cycle through the describing function method. We have seen how we can break a non-linear equation into a set of linear and non-linear element, and from there we can find out the total Kerres equation of the system and analyze the system for its various properties. So that's all for this session.